it doesn't work on on complex atoms. But Bohr still won Nobel Physics Prize due to his because he's the first person who actually incorporates the idea of quantum physics into the atomic model. So this model, the main use of this model is that it has like some kind of reference to all other models that come after Bohr model, since Bohr model can correctly depict the spectrum made by hydrogen atom.
All right, let's discuss the Heisenberg Uncertainty Principle. So the Heisenberg Uncertainty Principle ties a lot into the matrix mechanics, right? So Heisenberg wanted to describe the ideas in Bohr model with experimental data. And so he published a paper. It didn't directly mention matrices, but it mentioned kind of a recipe for them. It wasn't explicit. But it was Max Born who looked at his paper and formalized the notion of matrices. And so a key property, if you're familiar with matrices from like math class, you might know that they don't commute. So like if you have a matrix P and a matrix Q, and we multiply them P times Q, that is not the same as multiplying Q times P because of the process of matrix multiplication. And Heisenberg sort of took this idea and tied it into the quantum mechanics right here. And you can create like a matrix for position, which is P, and then a matrix for momentum, which is Q. And so you have QP minus PQ equals I times H divided by 2 pi, right? Where H is Planck's constant, if you remember that from before. And hopefully you're familiar with I, square root of -1. And so you have that identity right here. And it aligns with Bohr model prediction and other experimental results. And so there's some key ideas with the uncertainty principle, which relies on the incomputableness of the matrix, right? Incommutableness, where the matrices can't, P times Q doesn't equal Q times P, right? And so the order of measurement will determine what result you get with the position and the momentum. So if you measure the velocity and the displacement in a different sequence, you will get a different result. And the uncertainty is actually the basic property of particles, which is what scientists figured out. So this is like the heuristic of the uncertainty principle of Heisenberg's work. And there you can see the equation, the key equation, right? And there's H bar. And H bar, you can see the constant H bar, which is just H over 2 pi, which is a key constant that occurs. Hopefully you saw the 2 pi in 2 slides ago. We had I times H divided by 2 pi. So here that reoccurs in H bar. So the way that this works, to my understanding, is that if we have like delta x, let's say that that's some alpha times 10 to the minus 35th power, right? Because H bar is on like 10 to the minus 34th power. So if we take that delta x and we divide that out, then you should get some kind of alpha times 10 to the 0th power because it's divided by 2. It depends which alpha you choose, but you can get like some 10 to the 0th power, right? And so that is, so for the momentum, that's just some positive constant, right? Compared to like that huge 10 to the minus 35th power, that's a very precise measurement for displacement. But momentum, if it occurs on 10 to the 0th power or 10 to the 1st power, that's a very imprecise measurement. So we measured the displacement very precisely, and that led to a very imprecise measurement of the momentum using this Heisenberg inequality right here. Delta x, delta p is greater than or equal to h bar divided by 2. So you can experiment with that a little bit mathematically, right? But here you can see on the slide, the more precise you measure the displacement, the more imprecise you measure the momentum.
So can I do some like more like a visualized approach? So let's just imagine you want to determine an location and velocity of a particle, let's say. But if you want to determine, you have to like you have to observe it first. And how do through any method, you have to like send some kind of electromagnetic wave to determine its velocity or its position. But once you emit that EM wave, it already gives this atom give this particle an extra energy. So if you shoot an EM wave to a particle, you know its location, but this EM wave gives it extra velocity, so you cannot know. So it doesn't really know its velocity. It's just like the process of observing something changes its property. However, later scientists will find out that it's not because it's not only caused by like human observe. So it seems like naturally everything is uncertain. Everything have some certain degree of uncertainty.
So after Schrodinger has his matrix equation, he came up with other ideas and ties this into de Broglie's the matter wave properties. So let's take a look at what wave functions are. Wait, actually, yeah, next slide, please. So, so that's how he tried to look at de Broglie. Who described everything as waves. Everything can be treated as waves. But Schrodinger thought, what is it actually? Is it like a real property, or is it just probabilistic? And so then he devised a set of method to calculate the wave. So basically, ended up it's very useful for determining where a electron might be. So that's how electron clouds. Maybe you learned it in chemistry. It's how we got those. Yeah. So let's take a look. So first of all, center of this is wave function. How you look at a wave function is that the horizontal axis is the position of where a particle might be, and what is the amplitude or the height of that is it actually ties into the probability of where a particle might be, but you might notice that it can be negative at times. So how you calculate the probability from the wave function is you use wave function squared. And you are seeing that these wave functions are dancing around on the right. That's because they are changing over time, much like in classical, we see a oscillating ball here. So it has time as a factor and position as a factor. And Max Born, as you see on the slide, is who actually explained that you have to square the wave function to get probability. Long after Schrodinger came out with how to with the wave equation, but Schrodinger's equation is not this. Schrodinger's equation will give us how what a wave function would be. So let's gain some understanding in the next slide. Oh yeah, this is another how we get the a wave function of hydrogen. If the color is if it's more positive or is brighter, there's more probability that a particle is there, and you can see the wave function is represented by psi. It's a really weird notation, but you can see it right there. And yeah, these are really beautiful graphs that you can make with wave function, and it's 3D. Yeah, it's pretty cool. It's much look like a cloud and the region of probability. Right. And this is the Schrodinger's equation on the top left. And it looks very weird, but you can see E is just the total energy. And after E, that weird notation is the psi. That's just a wave equation. And it can take several forms, but we will go through that later. And you see some constants like h bar. H bar is Planck's constant divided by 2 pi. And we just mentioned it. And why there's a bar, we can also talk about it. and for yeah, and d squared over dx, that means derivative in calculus, and v is potential energy. And you might find out this is just a energy conservation equation. So in classical mechanics, we have a system of a system has constant energy, and so kinetic energy and potential energy translate, but their total will always remain the same. And this is still following the rules that we normally have, but we are trying to get the wave equation. So what Schrodinger's thought process was having this wave equation, but he used the energy of the system to calculate this wave equation. So our purpose here is getting the psi. And there's a little working backwards method here on the bottom left. We are working backwards from the psi. So we have our psi as in the purple, you can see there's a wave function equals e to the I is imaginary. It's imaginary axis on the amplitude that I just mentioned. It's because like you can think of it as wave function is not actually observable. You have to use this total energy thing to get it. So you can maybe if that makes sense to you, that's why the I is there. And then you have 2 pi x over lambda is the wavelength. Wavelength is what de Broglie got in his matter wave wave series, and minus omega t. Omega t is basically ties into the oscillative property of the wave function. And but here we are treating it as a constant, so we are not considering time. We're not considering the funky dancing curve. We're just thinking of it as like time independent species. So if we take the derivative of this wave function, it's basically a simple like derivative, and then because like if you taking calculus, it's really interesting because the derivative of e to the something is that something times itself. And wait,
Wherever you'd like.
and it's not that something, it's the I 2 pi over lambda times x, and that I 2 pi over lambda comes down. And then we can substitute the original wave function into that. And we then take the second derivative. Then what we find is that if we do some algebra, we can find the second derivative of the wave function equals negative momentum squared over h bar squared psi. And if we look at the original energy equation, we find that the kinetic energy can actually substitute into momentum over 2m. So you see that momentum purple p squared over 2m. We can substitute the entire wave function derivative into that. And then what we get is a pure relation between the wave function at some constant in the system. So that's how Schrodinger made it possible to calculate the wave function. And so what is h bar, right? So it's just that 2 pi you see over there, because it's basically a period of thing, and they just simplified it as h bar is just h over 2 pi for like easy of writing. And then we get this wave equation, and right, so bottom right, there's the probability. It's basically a wave function squared, and it gives us the probability of a particle. And you see that it's taking a cosine form. It's still like the wave equation, but it's in the trigonometry form. So with Schrodinger's equation, there spurred a lot of debate. So we will talk about how we are using how physicists are using Schrodinger's equation like on a daily basis. But what does it mean? Spurred a lot of debate, and there are many interesting thought experiments that's detached from the reality, from really the application of it. But it's interesting and it's philosophical. So does the wave equation just describe only one particle, or is it like a system of particle altogether and doesn't really mean one? And then there's the measuring of the wave of the particle causes the wave function to collapse. This is a very important concept because it's a wave, right? You're in quantum mechanics, you're treating the particles as a wave. But if you can observe that matter, it will be only at one position. It cannot be at you can't see it at all positions at time. But we think like that, but we can't see it like that. And that's an important concept that we will go over in the future, I think. And that ties into Copenhagen interpretation and spurred many debates from famous scientists like Einstein and Bohr and Schrodinger himself.
So the Schrodinger's equation is perhaps one of the most important equation for quantum physics. So for Schrodinger equation and the matrix mechanics derived by Heisenberg, they are in some ways exchangeable. That means that you can derive from Schrodinger's equation to Heisenberg's matrix. So the reason why scientists prefers the wave function is because it's more easier to understand, because physicists have a good mathematical knowledge, but at that time not many physicists study linear algebra, so matrix is a new stuff for them.
Right. So there are actually after Schrodinger got equation, he realized that they're actually the same thing as a matrix equation. So that's a really interesting part. And quantum tunneling is the consequence of the wave equation. So let's first look at the graph on the right top. So that's what a wave function gives us. So if you have a particle in a confined space, maybe electron in bounded by an atom, there will be like energy boundaries for it, because if it takes energy to basically delocalize the electrons and like move it away. So, but the wave equation, with wave equation, we have a small probability that it can actually basically blip out of the boundary of the atom. So that's what we see on the bottom right. So there's a very small possibility that the atom can be outside of the boundary and just the electron can be outside of the boundary, or whatever particle it is. It can overcome any like energy barriers. So on the bottom left is a test of this actual phenomenon. So we said blip. So exactly how fast is it? Physicists think it's instantaneous. So they test this out, and it actually is. So there's a red line above, and there's a blue line below. So what this setup is basically shooting two lights, and one light is obstructed by a barrier. So physicists only expect the particle that's blipped or quantum tunnels will go through the barrier. And when the two light meet, they were calibrated to have the same wavefronts, so they were overlapping at the beginning. But if at the end there's any difference between them, they can observe this change in position of them, or change in changing the right. So based on this difference of position that the wave fronts are at, they can calculate the difference in a velocity. And they test this out, and tunneling happens instantaneously. But that the explanation of that is it's actually not faster than light, because they didn't actually travel. They were just like at a different position at the time. Of course, that yeah, so that's a very interesting phenomenon, and it ties into what we think of the macroscopic world. So what if you think that you can basically tunnel through the wall if you try a lot of times, because you're looking for that very small probability of transporting through the wall. But what de Broglie, this still ties back to de Broglie, because you have very small, if you have very big momentum, then, which means you have very big mass, and you have like very, very small a wavelength. So your position, wavelength is small, that means you're pretty certain that, it's pretty certain that you're here, you're at where you are. So also there are quantum states. Particles in the quantum world act very differently as the macroscopic world. So it's an entire it's a different world that we're looking at. So yeah, so you can't actually tunnel through the wall, but electrons can. Yeah, so this is the video.
So quantum tunneling has actually many applications in real life and other things. For example, the nuclear fusion of our sun, of stars. So in order to have nuclear fusion, the atom's nucleus, they need to get close enough. But in order to get that close, they need an incredible amount of energy that is bigger than their momentum. So due to the quantum tunneling, although the energy of the nucleus might be smaller, might be less, does not have enough energy, the quantum tunneling can still let them pass through and makes fusion. And also it applies to quantum biology, which is that is the electrons, the property of electrons that helps the quantum tunneling helps them to helps electrons to transfer through different parts of the systems, and it actually did a great job on helping to fixing stuff like DNA. And modern computers also uses like the idea of quantum tunneling to pass electrons. Sometimes electron will just pass, will just mysteriously get past like some other matters that they did not expect it.
All right, so at this point, we've reached the end time for the club meeting. So next time we'll try to elaborate a little bit more on the ideas covered this class and go a little bit into quantum computing and some applications of quantum mechanics. At this point, we will have to cut short because our time has ended. But nice job today, everyone.
Thank you.
Thank you.
Bye, Rohan.
Nice work today, Alan. We'll try to make sure we do some time management, maybe rehearse this or something next time.
Yeah.
But nice job. Nice job.
Right. Yeah. You too.
Right, see you, Alan.
I'll send you the recording. Oh wait. Oh yeah. I think.
When did you start recording today? You started recording a little bit late, right?
Yeah. Yesterday.
All right, just send me what you have and I'll upload that.
All right. Okay.
Bye, Owen.